Hey guys, welcome back to Problem Up Chem. In this video, we're going to start Unit 11, looking at uncertainty and error. Really important topic that's often misunderstood, but if we just are specific with our language, we should be pretty fine. Important to consider here that this is going to be really useful in your IA and being able to process your data effectively. So it's going to have that dual exam and IA use. Starting with the difference between quantitative and qualitative analysis. In qualitative analysis, we're going to have non-numerical data, which is going to be obtained from non-numerical data observations. This can include things like solubility, reactivity, color changes, but also things like mass spectrometry are also qualitative. Quantitative is taken from measurements made in the lab and have an associated random error because we're taking numerical measurements. This means it's important the way that we record that data. So results tables should include the quantitative data with units and uncertainties, and this should be recorded with appropriate precision. Now that will be determined by the pieces of equipment you're used. You can see in this table here, no units are included in the body of the table, all of the units and uncertainty in the title cells, which allows us to see that we've used appropriate precision in our recording. Talking of precision, this is a word that I see often used wrong, and it's often used wrong alongside another word, which is accuracy. So let's just lay down what these things really mean so that you can be specific when you use them. So we can use a simple target analogy that's going to help us visualize the difference between these. First, let's give a definition of precision and of accuracy. So precision refers to the closeness of the values we take, how much they agree with each other. This is independent of what the real value is. This is just how consistent we are at producing values using the experimental procedure we have outlined. Accuracy, on the other hand, concerns itself with how close the value that we have determined using our experimental method is to the real value, the agreement between the result of our measurement and the measurand, which is what we call the actual value. If we draw a few sets of marks on these targets, we can evaluate them based on their precision and accuracy. So if we put 3 marks on each, we can evaluate each of these groupings using our definitions. So if we say P for precision and A for accuracy, for the sake of ease, we can look at this first top left target and we see that they are both near each other, being precise, and near the center value, accurate. The second target is precise but not near the measured value, so that is inaccurate. The third target is accurate if we were to take average values but imprecise as we can't repeat those values. And lastly, the bottom right target has both imprecise and inaccurate because they are neither near the measured value nor near each other as measurements. Turning our attention to other key terminology that we need to be familiar with is significant figures. So as you may already know, numbers can be rounded to a given number, and that number has a certain number of significant figures. We could call this the certain figures or the known figures. These are the digits that we actually measure. And then we have one doubtful digit or number at the end of our value, which we are not certain about. In a calculation, when we use values of different significant figures, our answer can only be given to the minimum number of significant figures that we used for any value in our calculation. So we can't have values given as answers with very high significant figures if one of our measurement had, 1 or 2 significant figures. For example, in this measurement of grams, we have 5.431. That's 4 significant figures. And we could say these first 3 digits are our known digits. These are known with certainty. And this 1 at the end, because it's the last digit, is our uncertain or our doubtful digit. We are not certain that that is exactly 1. It could be larger or it could be slightly smaller than that. And that's where we get our uncertainty or absolute uncertainty from, plus or minus 0.001, in this case, the smallest increment of measurement used when measuring this mass. 2 other terms we need to make sure that we're able to define very specifically and use correctly are error and uncertainty. So error is really the difference between the results obtained in our experiment and the generally accepted value, which you might find in the data booklet or another literature value. If we have the benefit of having literature values or values obtained in a professional environment available, then that means we're going to be able to calculate the percentage error, which can also help inform our conclusion about whatever study we might be undertaking. Without a correct literature value, no useful comment can really be made. Uncertainty, on the other hand, occurs due to the limitations of the pieces of equipment we're using. So whatever equipment we're using, we're going to take measurements, and those measurements are going to have a specific level of uncertainty. For example, in a titration, we use a burette and a pipette, a balance, etc. And all of these things have an associated uncertainty. Now, we can look at uncertainty in 2 ways: as absolute uncertainty, which is the margin of uncertainty associated with the result of a measurement taken. So, for example, if we were to weigh something out and we got a value, it's going to be plus or minus some amount, like 3.45 plus or minus 0.01. Relative uncertainty tells us the ratio of the size of the measurement that we've taken compared to the absolute uncertainty. And the calculation for this is very simple. We're just going to take the absolute uncertainty of the measurement we've taken, divided by the value of the measurement, and then multiply it by 100. That gives both relative uncertainty and the relative percentage uncertainty, respectively. So we can take the example 12.25 plus or minus 0.02 centimeters cubed would be 0.02 divided by 12.25 centimeters cubed would be our relative uncertainty, and we multiply that by 100 to get our relative percentage uncertainty, which is 0.16%, given 2 significant figures in this case. The uncertainty of instruments is different for both digital and analog instruments. So usually it does say the uncertainty on the apparatus you're using, but in general, for digital instruments, the absolute uncertainty is going to be the size of the smallest increment that that apparatus lets you use. So in this example, where we have the scale, we can see that it allows to go to 0.01 grams. And so the absolute uncertainty for this scale would be 0.01. And so if we wanted to calculate the relative percentage uncertainty, we would do 0.01 divided by 16.43, which is 6 times 10 to the minus 4. And if we want the relative percentage uncertainty, then we just multiply that value by 100, giving us 0.06%. So for analog instruments, the calculations remain the same. However, our absolute uncertainty is, instead of the whole smallest increment, it's going to be half of the smallest division that the instrument can measure. So for example, in this view of this graduated cylinder, we can see the measurement says 43 milliliters. So the smallest division is 1 milliliter. 1 milliliter then means that the uncertainty will be plus or minus 0.5 mil. Our relative uncertainty, remember we just do absolute divided by the measurement. And if we want the relative percentage uncertainty, we just multiply that value by 100, giving us, in this case, 1% given to one significant figure. So what does this look like when we're calculating percentage uncertainty in results? Well, here's a table of results for some titrations, and we can see that we had 0.05 centimeters cubed was our uncertainty on the burette. Now, because we've had to take two measurements, the uncertainty has to be doubled because we were uncertain by the same degree at both of those measurements. So what does this mean for the percentage of uncertainty of the volume? So first of all, we would want to calculate the average volume by using our two titrations that were within 0.05 of each other, which gives us 10.88 centimeters cubed plus or minus 0.10. And then we calculate our relative uncertainty, again, absolute over the value, like given 9.2 times 10 to the minus 3 to two significant figures, and just multiply that by 100 for our percentage value, which is 0.92% to two significant figures. Okay, time to do some questions before we look at experimental error. So, what would the absolute uncertainty of this mass balance be? Pause the video to give yourself a moment for that. Pop 'em up! So we can see this digital balance has a measurement of 12.68 grams. And remember, digital instruments will have the uncertainty being equals to the smallest increment that measures, which is plus or minus 0.01. Next question then, using the same measurement, what's the relative percentage uncertainty of the mass recorded on the balance? Pause the video, give yourself a few seconds to work that out. Pop 'em up! So remember, relative percentage uncertainty is absolute over the value multiplied by 100, which gives us 0.08% to one significant figure. So the next question in three parts for this thermometer state the absolute uncertainty, the measurement including the uncertainty, and the percentage uncertainty. Pause the video to give yourself a moment. Pop 'em up! So as we can see, the smallest increment is 0.1 degrees, so we can quote that as 31.4 plus or minus 0.1. And when we do absolute over the measurement multiplied by 100, we're going to get our percentage uncertainty. Let's do a couple more questions in the same format, this time for a pH meter. Pause the video to give yourself a moment. Pop 'em up! Once again, a digital instrument, so we're going to take the smallest increment as our absolute uncertainty in pH. Our measurement is going to be 7.00 plus or minus 0.01 pH. And of course, for percentage uncertainty, we're going to do absolute over the measured value multiplied by 100, which is going to give us our percentage uncertainty of 0.1% to one significant figure. Last question then, an analog instrument, but the same three questions being asked. Pause the video to give yourself a moment. Pop 'em up! Now, remembering with an analog piece of equipment, we take half the smallest increment for the absolute uncertainty, quote the measurement in exactly the same way. Here we've got 63.5 plus or minus the absolute, and we calculate the percentage uncertainty in the same way we have before, doing absolute divided by the measurement multiplied by 100, which gives us 0.8% to one significant figure. Brilliant. So, experimental error. Now, when we talk about experimental error, we're talking about two main types. You have systematic experimental error, which is concerned with accuracy, and random experimental error, which is concerned with precision. So you can see the themes, what we started with defining accuracy and precision. Now we're looking at the types of error these can lead to. Systematic error is caused by things like zero error, like not zeroing your scale, not calibrating equipment, or just problems with the experimental design in general. Now, the way we can minimize these kinds of errors is to improve the design of our experiment and use our equipment properly. Random error has multiple causes, from things like measurement, parallax angles when looking through analog equipment, incorrect use of equipment, and we can minimize this by using the correct equipment and also repeating the experiment. So let's take a slightly deeper look at each of these in turn. Random error is called such because it is derived from uncontrolled variables in the experiment. Therefore, we're not able to remove these completely from any investigation. They have an equal probability of being higher or lower than the given measurement based on the uncertainty of the equipment we're using, hence random, and these can be caused by changes in the environment during the experiment, potentially misreading the equipment that you're using, or not completing enough trials. Now, we can reduce random error with such measures as repeating the experiment and especially using precise instrumentation. No measuring volumes in beakers. Compare the absolute uncertainty of a volumetric pipette, 0.08 centimeters cubed, to that of a beaker where you have plus or minus 5 centimeters cubed, and we can see how we would end up with a much higher percentage uncertainty using the beaker than that of the volumetric pipette. When it comes to systematic error, this is caused because of flaws in the actual experimental design, which also includes using the wrong equipment. And for that reason, these errors tend to shift the value obtained in one direction, either always getting a larger value or always getting a smaller value. And these can be broken down into three main types: instrumentation error, experimentation or method error, and of course, personal error. There are many examples here, and these are the things that we try and control as much as possible when writing our methods, such as heat loss, losing products in reactions, reading from the top of a meniscus instead of from the bottom of a meniscus in a burette, for example, or forgetting to zero the balance when you weigh something. These cannot be reduced by repeating the experiment. The only way we can reduce these is by designing our methodology to reduce them in the first place. Okay, time to test yourself out on random and systematic error then. First question: repeated measurements can reduce the effects of either random or systematic errors. Which one? Pause the video to give yourself a moment. Pop 'em up! Of course, we just said that systematic errors cannot be reduced by repeating the experiment, so the answer is, of course, random errors. Next question. A student reading from the top of the meniscus would be which kind of error? Pause the video to give yourself a moment for that. Pop 'em up! And of course, any error that will always push the answer in the same direction each time is systematic, because we will always read a smaller number on a burette than we would if we read from the bottom of the meniscus. So this is all very well. However, in any experiment, you're going to be doing multiple measurements, and you're going to be looking at potentially many steps which might have elements of uncertainty in them. So you need to be able to do what's called propagating uncertainty. And basically this just means taking account of all of the uncertainty at the different steps of our methodology. So there are two rules that you need to follow for this. They're quite simple. The first is, if you have two values that you are adding or subtracting, you simply combine their absolute uncertainty to give you their overall propagated uncertainty. I did this in the example of the titration earlier on in this video. The second rule is where we are going to be multiplying or dividing those. Now, it's not quite so simple here. When we multiply or divide, we have to add together the relative percentage uncertainties, not the absolute uncertainties. And this is going to be a key component that you use in your IAs. Let's look at some data from a calorimetry experiment and look at how we might propagate our uncertainty. So we're going to do our usual calculations. So obviously we've done 3 trials here. So we're going to work out our average temperature, which is nice and simple. We're just going to look at our average change in the temperature of the water, which we do as a normal calculation. In an average, we do not change the uncertainty. So it would still be plus or minus 1 degree as we haven't processed it. We've just taken an average. So next we would go about using our Q equals MC delta T equation from unit 5. And we're going to make a couple of assumptions. First, we're going to assume the density of water is 1 gram per centimeter cubed. And we're also going to take the specific heat capacity of water as 4.18 joule per gram per Kelvin. Plugging the values in from the results table, we get 50 multiplied by 4.18 times 7.2 equals 1504.8 joules, which is 1.5 kilojoules taken to 2 significant figures. So to propagate our uncertainty in this example, we've multiplied values. So our total relative uncertainty is going to be the sum of the percentage uncertainties of each of the values. So first we consider the temperature. So with temperature, we just take the absolute divided by the average temperature change times 100, which is 14%. And the percent of the volume is going to be 0.5 divided by 50.0 multiplied by 100, which is 1%. Now all we need to do is combine those two percentages, which gives us 15% as our propagated relative uncertainty. That doesn't tell us the whole story though, because that isn't a value in kilojoules. So the last thing we're going to do is we're going to convert that back into an absolute value so that we can quote our final value with its absolute uncertainty. And this is quite simple. We're just going to multiply that value that we just got in percentage by the value in kilojoules, which gives us 0.18 kilojoules. And so we can quote our value as 1.5 plus or minus 0.18 kilojoules. You'll see in the calculation, I converted the 15% to a decimal for sake of ease. That's where I got the 0.15 from. Of course, this is just an example, but it could be used in a multitude of different experiments. So if we get this far and our experiment has a literature value available, we may also be able to do a percentage error calculation. And this effectively shows us the difference between the value that we have found in our experiment, the experimental value, versus a literature value. And we calculate this by taking our experimental value, subtracting the literature value, and dividing it by the literature value, multiplying it by 100 to get a percentage. These values can be negative and they can be positive, but they won't be appropriate for all experiments because not all experiments may have literature values for what's being investigated. Let's have a look at an example of a question. In this question, we found an experimental value for the enthalpy of neutralization, and we want to compare it to the literature value. So all we're going to do is use the value that we have found, which is negative 49.6, and we're going to subtract the literature value and divide by the literature value to give us a percentage, which in this case is negative 12.9. Usually a high percentage error indicates the presence of systematic errors unless the processing of the random errors accounts for this percentage difference. If it does not account for that percentage difference, then there must have been some kind of systematic error that accounts for it. In this case, that would be heat loss, as we were doing a neutralization reaction. Okay guys, so there are questions to do on this, but remember, it's much about understanding the language and using it properly in your IA with this. Thanks again for joining me. Don't forget to like, subscribe, get notified for new videos, and share the channel. And as always, practice makes slightly better.